In this video, we're going to be talking about Euler circuits. Now, that is how you pronounce it. A lot of people say Euler, but it's the correct pronunciation, according to what I've seen, is Euler. And Euler was a very famous mathematician. He lived in the 1700s, and he was one of the most important mathematicians of his time and one of the most prolific mathematicians ever. His collected works fill 92 volumes, more than anyone else in the field. So he was a very important mathematician, and he is sort of the name of this circuit because this is one of the things he came up with. If you recall, if you watch the supplementary video I posted in the introduction to graph theory, it gave a big history of the start of graph theory and how Leonard Euler was really the father of graph theory. So what is an Euler circuit or Eulerian circuit? It's a circuit that contains every vertex one or more times and every edge exactly once. One or more times. So the idea, the emphasis is, can we cover every edge in a graph? Can you walk around a graph and cover every edge and then come back to the beginning, which is why it's called a circuit. There's also something called an Eulerian path, which doesn't have that requirement. And so every edge exactly once. Right, so that's a really important thing. We cover every edge of G exactly once. Now, to do this, here's a simple example. Let's take a look. Right, we can start at one of these vertices. And go like that. And we've just found an Eulerian circuit. So there are many of them. We can undo that. And we could start here. Right, but you notice, just because I'm starting in different ways and maybe I do these two endpoints on the side in a different order, it's really the same thing. We've covered all of the edges. Now, not all Eulerian circuits are going to be this simple. So an important theorem in graph theory is that if a graph has an Euler circuit, then every vertex of the graph has a positive even degree. And we're going to prove that by a proof of contradiction. So we're going to say, suppose not. That is, you need to suppose the negation. That is, suppose there exists a graph, G, let's give it a name, with an Euler circuit, that has a vertex with odd degree. I'm going to call that vertex V, odd degree. Remember, to do that properly, you need to remember how to negate a universal conditional statement. Okay, so we've got some graph. And we've got our vertex V, and V is connected to the graph an odd number of times. I don't know how many that is. It could be 1, it could be 3, it could be 5, I don't know, but an odd number of times. An important thing to note here is that without loss of generality, V is not going to be the start or end index, or start or end vertex. And we can say that because, again, if you recall a graph, if it has an Euler circuit, that's what we're supposing, right? We're supposing we have a graph with an Euler circuit. And that means if we have this circuit, if this is V right there, and I normally want to start at V, well, okay, I'm just going to move over and start at this one instead, right? It's a circuit, so whether it goes starting at V or not, it's going to cover all of the edges. So if V was originally a start endpoint, we're going to move it. We're going to say, no, let's pick a different start endpoint. It's a circuit, so any of the vertices on the circuit could be the stop endpoint. Let's leave V out of it. Okay, so since it has an odd degree, then the degree of V is going to equal 2q plus 1 for some integer q. And that's the definition of odd. We have an odd degree, so I know the degree is odd. So this is important. We have the degree is equal to 2q plus 1. And we're going to have to move on to the next page to finish this, but we want to remember that that's the number of vertices we have. We have the degree is 2q plus 1. Okay, so here I've redrawn this little picture of sort of what's going on. And I want to, for the crux of this graph, the idea is we're going to be traveling through V a lot. So I want to do an example. This is not a proof. This is an example to see the idea. So we have odd degree. What if had degree 5, right? And again, these are all going to some other vertices in the graph. So sort of got this big cloud graph here. Now the idea is if V is not the start or the end, I don't start there, but I can come in on one of these edges and then leave on another. So that was one pass. And then I can come in on another edge and leave on another. And so remember, we have 2q plus 1 edges. In this example here, q is 2. Right, so we have 2 times 2 plus 1 edges equals 5. We have 5 edges, and that is correct. Okay, so I can go through the 2q edges one at a time like we just did, right? Come into V, leave V. Come into V, leave V. But notice there's a single odd one left, and in order to follow that, I'm going to have to start somewhere in my graph, follow it in, but then I get stuck. And I'm stuck at V. I can't leave V because the red lines have already been used. So I can't use it. I'm stuck, but we said it wasn't the beginning, the start or end vertex, and there's my contradiction. So let's write this up a little bit more formally. That's the proof idea, but now we want to be a little bit more formal. We say that if we pass through VQ times along the circuit, each time removing or coloring or in some way marking the edge that we've used. Removing it's easy, so each time, because we can't use that edge again anyway. Then V will only have one edge left. And we will be at a different vertex, right? Just as I showed in our example. Because we went through VQ times. So if we follow that last edge and go to V one more time, will get stuck there. But we said it wasn't the start or end vertex. And there's our contradiction. Right? So if a graph has an Euler circuit, then every vertex of the graph has a positive even degree. Okay, so what is the contrapositive? Remember, we know that a vertex that has an Euler circuit, then a graph that has an Euler circuit, then every vertex has a positive even degree. And we know the contrapositive is also true if the statement is true. So what is it? You can rewrite it by saying if some vertex in the graph has odd degree, or 0 degree, right? 0 degree, what would that mean? That would mean it's sort of a little island, and you're never going to get there because there's no edges going to it. Then the graph does not have an Euler circuit. All right, so that is the contrapositive. And since we proved the statement already, we know this is true as well. So we know if there's a vertex with an odd degree or 0 degree, then there's no Euler circuit. So how about this one that we're looking at here? Does it have an Euler circuit? Well, the way you find out is you look at the degrees. So it's very annoying. Degree of 2, degree of 2, degree of 3. It's not going to have an Euler circuit. However, we can find the vertices of odd degree. There's one, and there's one. Oh, and here's one too, degree of 1. So this does not have an Euler circuit. Vertices 2, 7, 9, and 10 are odd, of odd degree. So that was the contrapositive. What about the converse? Now you should be able to do this. You should be able to pause the video and write down what the converse of this statement is. And that converse is if every vertex of the graph has a positive even degree, then the graph has an Euler circuit. Now, is that true? We know from doing our Boolean algebra that the converse is not necessarily true. So if a statement is true, the converse could be true, but it's not required to be true, right? So in this case, unless the conditional statement is a bijection, meaning it's an if and only if, in that case, it would be true. But here, this is not guaranteed to be true, and in fact, it is not true. See if you can think of an example, a counterexample to that. I'm going to do proof by counterexample. So I'm sure there's many an infinite supply of graphs you could come up with. This is the simple one that I like. All right, every vertex has degree 2. But there's no Euler circuit because we cannot jump from one component to the next. All right, so there's a problem. So the converse is not true in this case. And next we're going to see a really important theorem that is a very important theorem in graph theory. And that's this notion that a graph G has an Euler circuit if G is connected and if every vertex has positive even degree. So pretty much, while the converse itself isn't true because it lets you have graphs that are not connected, if you fix that, you will get, if you force them to be connected, then it is true that if it's connected and every vertex has positive even degree, then there will be an Euler circuit. Now, unfortunately, this is a very complex proof that we're not going to do today. However, I will link, I'll include a link to a proof in the video description. Okay, this is a very important graph and it's used a lot. So this is important, it's just complex and we don't really have time to go through that today. So last slide here. Which of the following have Euler circuits? Well, again, I'm just going to go and I'm going to start counting edges. Start counting the edges coming into vertices. So A has a degree of 2, B has a degree of 3. Whoops. Right now, I can rule this out. It does not have an Euler circuit because of that 3. Let's do the second one. We've got 2, 2, 1, 2, 3, 4, 2, 4, 1, 2, 3, 4, 4, 2, and 2. Hey, everything has an even degree, which means an Euler circuit exists here. All right, so this one has an Euler circuit.